So here is a summary of what we have so far. We have defined this function f of v comma I to be the cost of the shortest path from the given global source to any arbitrary vertex v, which uses less than or equal to I edges. And we also have a recurrence for it. F of v comma I is the minimum over all the predecessors of v. Predecessors of v are the vertices which have directed edges into v. For each predecessor, we calculate f of that predecessor comma I minus 1. This is the shortest path cost from the source to that predecessor using less than or equal to I minus 1 edges, and to that we add the weight of the edge from x to v. That is the final edge along that path, and if we take the minimum of the sum across all the predecessors of v, we should get the optimal value for f of v comma I. Now suppose there were two predecessors of v, let's call them x, let's say x and y. It is possible that in the graph there could be a vertex which is a predecessor of both of these. Let's call this vertex as z. So in trying to calculate f of v comma I, we would need the values of f of x comma I minus 1 and f of y comma I minus 1. But how do we get the values of these? To get the value of f of x comma I minus 1, we would need the value of f of z comma I minus 2, and likewise to get the value of f of y comma I minus 1, we would need the value of f of z comma I minus 2. And of course there could be many other vertices in this graph. I'm just showing a simple example here. So notice that the worker who is responsible for calculating this value has to call someone else under him or her to first calculate this value, and the same thing is going to be done by this peer worker. This worker will also call someone else under him or her to calculate this value, and notice that both of these are essentially the same subproblem. So the same subproblem is going to be handed over to multiple people in this imaginary corporate hierarchy if we were to try to implement this in a naive way. So we have this scenario here of overlapping subproblems. There is going to be a lot of redundant work done in this corporate hierarchy if we try to solve this recurrence equation in the naive way. We also know that this way of defining the function has the property of optimal substructure. So because we have optimal substructure and overlapping subproblems, we are naturally led to using a dynamic programming based strategy to solve this recurrence equation bottom up, avoiding repetitive work. So we will start from the smallest subproblems and build up the solutions to larger and larger subproblems until finally we have the value of f of destination comma k plus 1. Right? Remember, the original problem had at most k stopovers, which means at most k plus 1 edges along the shortest path from the source to the destination. So how many unique subproblems are there? If we look at the first parameter v, let's assume that the vertices are in the range from 0 to n minus 1. So there are n cities in the graph that are given to us. Their IDs are from 0 to n minus 1. The second parameter is the number of hops. So the number of hops could vary from 0 all the way up to k plus 1. We can't go beyond k plus 1 hops. So in terms of the combination of the two parameters, there are n choices here and there are k plus 2 choices here. So this means we have n multiplied by k plus 2 unique subproblems to solve. So let's build a table which has a cell for every unique subproblem. So the first parameter v can range from 0 to n minus 1. The second parameter I can vary from 0 to k plus 1. So if we imagine this table with n multiplied by k plus 2 cells, then each cell in this table represents a unique subproblem which we have to solve, and finally we want the value of f of destination comma k plus 1. So how will that overall problem get mapped to this table? Well, let's say the ID of the destination is somewhere here. We basically want the value that is stored in this particular cell. Let's say this particular cell represents the overall problem that we want to solve, and the value here is something we want to be f of destination comma k plus 1. So what is the right way or the right order in which to solve all these subproblems in a way that we successfully manage to compute this value? Well, in general, we have to make sure that when we come to any vertex, let's say, or any subproblem, f of v comma I, let's say this is f of v comma I, this particular cell, we should have all the subproblems that it depends on solved, so that the values for them are available which can be used to compute the value of f of v comma I. So where are the predecessors of v going to be? Well, the predecessors of v could be any of the vertices of the graph. We don't know. Except for v itself, any other vertex could be the predecessor. But we know that f of v comma I is going to depend on f of x comma I minus 1, right? That's what we had here. So we need to ask, where is f of x comma I minus 1 going to be found in this grid? Well, it's going to be found somewhere in this column. Right, this column represents I minus 1 hops. So we are going to have some predecessors of v, and their values, let's say this is one of the predecessors of v. This value might be used to determine this. Maybe this is another predecessor of v. So this value will also will also influence the value of f of v comma I, and likewise there could be other predecessors whose values can also influence the value of f of v comma I. We have to consider all of those options and pick the one which is the best. So since the value of any cell seems to depend on a bunch of entries in the column to its immediate left, the natural way to solve these subproblems is to fill up this table column by column from left to right. That will ensure that when we come to any cell, the subproblems that it depends on would already have been solved and the solutions to them available in the column on the immediate left. So let's start by filling in the table with the leftmost column, which is column 0. What values are we going to put in here in the leftmost column? So let me mark the fact that we have to allocate a two-dimensional table of size n multiplied by k plus 2, and since we are trying to minimize the value of f of v comma I, this is a minimization problem. Let's initialize the table entries by default to infinity. Right, as soon as we find that there is a cheaper way to get to a particular vertex using a certain number of hops, we can always bring down the value from infinity down to whatever the value that we find. So by default everything will be initialized to infinity. So let's think now about filling in the leftmost column. So what does the leftmost column indicate? The leftmost column indicates entries of this form: f of v comma 0, since we are talking about column 0 here. So what does this mean? If we go back to the English definition of f of v comma I, this would mean the cost of the shortest path from the source to v using less than or equal to 0 edges. Now how can there be any path that uses less than or equal to 0 edges? There obviously cannot be any path from the source to v that uses less than or equal to 0 edges. So basically the leftmost column is going to be filled with infinity values. So this is in general going to be infinity as long as the source and v are not the same. But if we ask this question for f of source comma 0, what is the cost of the shortest path from the source to the source which uses less than or equal to 0 edges? Well, that cost is obviously 0. So if we pretend that this is the source vertex ID here, so this is the row for the source, this value here could be 0, but all the other values in this column will have to be initialized to infinity. So let me mark all of these values as infinity. Now let's fill in the next column. Let's say that's column 1. So when I come to say when I'm looking at this particular cell here represents the value of f of 0 comma 1. So this is basically the cost of the shortest path from vertex source to vertex 0 using less than or equal to 1 edge. So we have a vertex 0, we have a vertex called source. We are asking what is the cost of the shortest path from the source to vertex 0 that uses less than or equal to 1 edge. So if there is a direct edge from the source to vertex 0, f of 0 comma 1 will be the cost of that edge. Otherwise there is no way to get from the source to 0 using less than or equal to 1 edge. So notice that this value f of 0 comma 1 in terms of the recurrence would be the min over all the values, all the predecessors of 0. So 0 might have a bunch of other incoming vertices in the graph. We look at each of them and we look at the values of f of whatever the IDs for them are. Let's say the ID for this vertex is x. We look at the value of f of x comma 0, and then to that we add the weight of the edge from x to vertex 0. Right here the 0 represents the number of hops, here this 0 represents the ID of vertex 0. So notice that this value will in general be infinity, since the leftmost column is populated with infinity values. So in general for all predecessors except for the source itself, calculating this sum is going to result in a value that's equal to infinity, because f of x comma 0 is infinity. But for the source itself, we know that f of source comma 0, if x was the source itself, f of source comma 0 is 0. So if there is a direct edge from the source to vertex 0, the cost of that edge, the weight of that edge, will become the value of this sum. And that is what we will pick to be f of 0 comma 1 if we are taking the min across all the predecessors of vertex 0. So the value that will be stored here is basically the value on the weight of the edge from the source to vertex 0, if there is an edge like that. Otherwise it's going to be infinity. And so we can fill in column 1 like that. One question to ask here is, what should we fill in for this particular cell? What is the value of f of source comma 1? Right, that's the value of this particular cell here. Well, f of source comma 1 is nothing but the cost of the shortest path from the source to the source using less than or equal to 1 edge. Now, in a trivial sense, every vertex is the predecessor of itself with a cost of 0 on the edge from that vertex to itself. This is not just true for the source, but for any vertex v. We can treat v as its own predecessor with a cost of 0 on the edge from v to itself. So this means that if we want to compute f of v comma I, the baseline that we can start with is basically f of v comma I minus 1. So f of v comma I can be no larger than f of v comma I minus 1, because if there is a if there is a way to reach from the source to any vertex v using less than or equal to I minus 1 hops, that particular way is also a way to reach vertex v from the source using less than or equal to I hops. So we can start out by assuming f of v comma I is equal to f of v comma I minus 1 for any v and any I, and then we can see if we can improve it further. So in that sense, this 0 in the table can be directly transferred or copied into this cell here, because that's the baseline for f of source comma 1. F of source comma 1 can start out by being initialized to f of source comma 0. So in general, any cell f of v comma I can first borrow the value in the cell to its immediate left, and then we look at the actual predecessors of v in the graph and see what the cost of the shortest path through them is, and if we get a better cost, then we update it. So this means that when you're looking at a general cell, let's say f of v comma I, the value here can start out by being initialized to the value in the cell to its immediate left. And in general, that's true for any column. When we are thinking of filling in column I, for example, all of the values in column I can start out by being equal to the values, the corresponding values in the column I minus 1. And then for each vertex in column I, we look at the actual predecessors in the graph and see if the path through them, if any of them, leads to a better shortest path, a cheaper path to them, and if so, we update the value. So let's go back to writing the code here. We had the initialization that was done here, and now we have to actually write the code for the for filling in the whole table, the remaining columns from column 1 to column k plus 1. And remember, the column numbers here represent the hops. So we will be filling in the table entries, the shortest path values, for larger and larger and larger values for the number of hops. So let's fill in the table column by column. So let's say for the hops varying from 1 to k plus 1, right, or the column number varying from 1 to k plus 1, we have to write the code here now to fill in the entries in the column corresponding to the whatever the hops variable is. So how do we do that? Well, we'll first start out by initializing the whole column to the column on the immediate left. So that's the baseline. So for each vertex v in the graph from 0 to n minus 1, we will set for that table the value of the cell at row v and column equal to hops will be initialized to the value in the preceding column for the same row, right? This is the baseline that we are starting from, which I talked about a few minutes ago. And now we have to fill in the values by looking at the real predecessors in the graph. Now let's think about this a little carefully for a moment. Does it matter in what order we fill in the entries in a particular column? Since the value in a particular cell depends only on the values in the preceding column, it does not matter, we write this down to make this clear, it does not matter in what order we fill in the values, within a particular column. So we could go top down, we could go bottom up, or I could just pick the vertices arbitrarily in that column and set the values for those vertices in any order I want. What is even more subtle is that even for a particular vertex, it does not matter whether I look at all of its predecessors in one shot or whether I look at them one at a time with some gaps in the middle. So what I mean by that is, if let's say vertex v has 3 predecessors in the graph, so I have some baseline value for f of v comma I, which is basically f of v comma I minus 1. Now I look at the first predecessor. Basically I'm looking at this edge from the predecessor to v. I look at the f value here for the predecessor, I add the weight of the edge from that predecessor to v, and I see if the sum is better or smaller than the existing value of f of v comma I. If it is, then I'll update the existing value of f of v comma I. Now having done that, I could now do some go and do some other work on some other vertex, and then I could come back to this vertex later and now look at the second edge from the second predecessor to v. And I could again do the same calculation. I could find the f value. I could look up the f value here, which should be available in the preceding column. I add the weight of the edge into v, and I see whether the sum now is a value that is lower than f of v comma I or not. If it is, I update f of v comma I, and then I go somewhere else and I do some other work, and then I come back later and I look at the third predecessor. I look at the f value. I add the weight of the edge to v to that f value, and then I see if f of v comma I can be lowered by that, and if so, I update f of v comma I. So it's not necessary that I had to look at all 3 of these predecessors together. Now why is this important? This is significant because if I don't have to look at my predecessors in one shot, that means I don't need to build an adjacency list for the graph in my code. If I had to look at all my predecessors in one shot, then I would need an adjacency list structure to tell me who my predecessors are. In fact, this adjacency list structure would record my incoming neighbors, not my outgoing neighbors, which is what I generally record when I build the adjacency list for a graph. But I would need an explicit adjacency list structure to tell me who my incoming neighbors are. So that kind of structure has to be built at the very beginning of the code. But I don't need that. I can look at the edges in their raw order in which they were handed to me in the edge list, in the input edge list. I could look at each edge one at a time. So let's say I'm looking at the edge from U to V. When I look at this edge, I know there is a weight associated with a cost associated with that edge. I could at that point set the value of f of v comma I to be equal to either its either it doesn't change its value, or it could be lowered potentially to a value that is f of u comma I minus 1 plus this w. Right? If f of u comma I minus 1 plus this w equals a number that is smaller than f of v comma I, then I can update f of v comma I to be that. So I can say f of v comma I is the min of, let me erase this here, f of v comma I is going to be the min of f of v comma I and f of u comma I minus 1 plus w. So let's go back to the code and write this in. So I'm going to look at the edges of the graph in any order I want. So I could literally look at them in the order in which they were given to me in the edge list. I'm just going to assume that the edge list is called edges here. So for each edge, for each raw edge in the edge list, I could set or update rather the value of table of v comma hops. Right? Remember, hops is the column number that I'm in. I could update this to be the min of whatever it is right now and the alternate value, which is the value table of u comma hops minus 1, right? This is f of u comma I minus 1 plus the weight of the edge from u to v. So if I do this update for each edge in my graph, I would have updated all the f values in my current column number, which is given by the hops variable. So having done this, I could then go back and increment my hops value, which means I start filling in the values in the next column number to my immediate right. So this is what we keep doing until we have filled in the whole table. And at that point, the value that we wanted for the original problem, which was f of destination comma k plus 1, should be sitting in the rightmost column. So we just return that value, which should be sitting in the table entry corresponding to that particular vertex ID, that's the row number, and the column number, which is k plus 1. Right? Remember, k is a number that is given to us as part of the input. The source is also given, the destination is also given, and the IDs are given of the vertices from 0 to n minus 1 apart from the raw list of edges. So what is the time complexity of this algorithm? Well, let's look at the main loop first. We know that this for loop, this outer loop where we go column by column, this is going to run k plus 1 times, and each time it runs we are going to be spending order n time setting the baseline values in that column, and then we are going to iterate over each edge in the graph. So that's going to be order m time to do that, since there are m edges assumed to be in the graph. For each edge we spend a constant amount of time. So we spend order m plus n time each time this outer loop runs. And since m is typically bigger than n, I could express the total complexity here as order of m plus n times k plus 1, which is roughly order m times k. Since m is more than n, I can write this as order m times k. Now we also had some initialization prior to that. We allocated a 2D table of size n times k plus 2, and we set these initial values in the first column. So that would have added just order n time. Initializing the table itself would have taken time order n times k. Right, so order n times k plus order m times k is basically order m times k, since in general m is going to be larger than n. Otherwise we could write it as order m plus n times k if we wanted to, but let's say it's order m times k. So that's the overall time complexity. What is the space complexity? Well, the size of the table that we are using is n times k plus 2. So the space, the total space that we will be using is order n times k plus 2, which is order n times k. Now you might notice that when filling in the table, the values in any particular column depended only on the values in the preceding column. We didn't need to look at columns to the left of the preceding column. This means that we can optimize the space further by working with only 2 columns at a time. And this is a trick that I have done before. If you remember the pre-class videos on dynamic programming, we've done that a few times before. The way we work with only 2 columns is by initializing only 2 columns. So when allocating a 2D table, we will allocate the table to be of size n times 2 instead of n times k plus 2. Let's have only 2 columns. We initialize column 0 to infinity except for the row corresponding to the source, so this doesn't change. But when we look at the main body of the code, we want to now work with just 2 columns instead of all the columns. So we will still have the column number going from 1 to k plus 1. This is the hypothetical column number if the entire table had existed. But since we actually have only 2 columns with, let's say, indices 0 and 1, when we are looking up the entry or setting the entry in any row or column number, we will have to take the column number and do a mod 2. So this hops has to be replaced by hops mod 2. This hops minus 1 has to be replaced by hops minus 1 mod 2. And in the same way, in this for loop as well, this hops has to be replaced by hops mod 2. This hops has to be replaced by hops mod 2. And this hops minus 1 has to be replaced by hops minus 1 mod 2. And the final value that we will be returning will be stored at table of destination, comma k plus 1 mod 2. So wherever we are referencing or using column variables, we have to make sure that we take that particular column variable and do a mod 2, and that will make our column number map to one of those 2 columns which we have allocated. So we will keep switching between those 2 columns as the execution of our algorithm proceeds. So this is going to bring down our space complexity from order n times k to order n, since we need only 2 columns. The time complexity won't change, however. It's still going to be order m times k. This dynamic programming based algorithm that we designed to solve the given problem, the single source shortest path problem, although we also had a constraint here on the number of hops we could use along the shortest path, But this algorithm is called Bellman Ford algorithm. And again, it's not a coincidence that the name of Bellman is associated with this algorithm, since he was the one who coined the name dynamic programming, and he was working on building lots of dynamic programming algorithms. So the Bellman Ford algorithm, like Dijkstra's algorithm, calculates the shortest path distances from a given source to all the other vertices in the graph. But while Dijkstra's algorithm cannot look at the constraints of the form that we were given, that we can't use more than a certain number of hops, Bellman Ford algorithm can handle that type of constraint. Now, if we had let Bellman Ford execute for more and more and more number of columns, how high could we go? So how high could we make the number of hops? We know that the number of hops given to us were restricted to k plus 1 in this problem, but we also know that this value can go at most to n minus 1. Right? Once we cross n minus 1 hops, the table entries are not going to change, because any shortest path in the graph from a given source to a given destination can use at most n minus 1 edges. We saw earlier that if the edge weights are all positive, there can't be any cycles in the graph. So because there can't be any cycles, we can't go beyond n minus 1 hops. Even if we did, we would not be doing any useful work, because the values that we would get in those column numbers beyond n minus 1 would be no different from the values in the preceding columns. And so the maximum that we can allow Bellman Ford to execute is up to n minus 1 hops, or n minus 1 iterations of this algorithm, after which we will have the absolute shortest path distance values written down in the rightmost column. So we could use Bellman Ford algorithm to compute the shortest path distance values from a given source to all destinations, regardless of the number of hops. We just have to make sure that it executes for at least n minus 1 times. Once it executes n minus 1 times, the shortest path values would be written in the rightmost column. Now, between Bellman Ford and Dijkstra, which one would you prefer if you only had to compute the shortest path distance values? Well, if you remember from an earlier video, Dijkstra's algorithm on a sparse graph took time order n log n. How long will Bellman Ford take if we were to keep executing it until the absolute shortest path distance values were written down in the column numbers? Well, if we were to continue Bellman Ford for order n iterations, in each iteration we took time order m plus n, so we actually had this complexity of order m times k. What we are saying here is that k is going to be order n in the worst case, and so Bellman Ford will end up being order m times k or order m times n. Right, this is the complexity of Bellman Ford in the worst case, and in a sparse graph this would be order n square, because m would be order n. So clearly order m times n is worse than the complexity we had for Dijkstra. Even on a dense graph, the complexity of Dijkstra was order m log n. So order mn is clearly worse than order m log n, and on a sparse graph clearly order n square is worse than order n log n. So Bellman Ford is in general more expensive than running Dijkstra's algorithm, which is why we would prefer Dijkstra's algorithm if we only had to compute the shortest path distance values independent of the number of hops. But because we had that constraint here that we can't use more than a certain number of edges along the shortest path, we saw that Bellman Ford came in handy, whereas Dijkstra would not be looking at the number of hops along the way.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews including back-end, full-stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today